So next Thursday's material is gonna help with last problem on number.
Yeah, so we'll probably get through step functions today. We'll probably do impulse functions on Tuesday. And then I plan for Thursdays just to do more examples. So by next Tuesday, you should hopefully have everything.
I know. You're on the sports underneath. I try to get the gym, and I think jeans change, shorts are sweaty and it's. You gotta wash your jeans more frequently, it's not good for those things. That's a real.
Cheap jeans.
Just wearing just, I think I found the best jeans I've done with that last one, even type of fits is Ariana, their work shoe. It's just enough flex, but also durable, so it enhances it. Like it fits my legs, the waist is like 6 inches too big, it fits my waist, just didn't the legs. What's that? Yeah, exactly.
I know you struggle too.
Not material.
Usually like answer the question separately and then do like the thing instead of. That's.
I hate it.
I know.
It came out of left field.
I heard still use too much. I was like, yeah.
It was an exam where you didn't know how to solve one of them. In like within a few minutes, so you were kind of awesome, you know. Each one took me at least 5 minutes to try to figure out how I'm gonna solve it. And then after that.
So, sounds good for sure. I would like, I've never had this.
The last one, the train.
I couldn't figure out the train. I was like, that one was like, dude, I think I put it right down. It was like, I would say like good acceleration.
At different points in the track.
I guess like, and then that was like the last day.
Which were the ones that you?
Linear one.
Just for the lessons.
Yeah, linear one.
Oh,
Got that one.
Question to ask.
I forget that one.
those two.
Yeah.
There's
The quality stuff.
You can, yeah, you know, spin. It's always been. I never realized this. So
The one that goes up now this much and then goes to the right.
Okay, no, no, that one was.
Yeah.
I know.
You know which one is over there? Velocity off the house, all the girls in the house. They both hit the ground, so that's the same velocity.
Like $990. I was in that. Like we go into the gas station.
That's why I said it.
Yeah.
You can prove it, but it takes so much time to prove it.
The hardest part
It's-
is doing the graph.
The whole thing is, like you throw, it doesn't matter what velocity you throw, the acceleration eventually catches up with gravity, right? So they both hit the ground at the same velocity. But I'm like 30 feet, like let's say a house is like 30 feet, I throw a ball down pretty hard, you know?
So being that way, because if you're. Yeah. I mean, what happened? Well, I think first it's like shooting.
Yeah, the train one. Split into 4 sections. Oh, I should try. When sign off those.
And then. Yeah, that whole news. I was like, I don't remember this exam. I don't remember seeing that exam, but anyway.
Here's the question, Steve. The curve linear, what the cars, Rosen? After you find. Yeah. You combine them, get one that. The acceleration.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. Good to see the sun. It was raining quite a bit today, although it's still freezing cold outside. So hopefully everyone is able to go back and get warm after this. Okay. All right, so plan for today, we're still on Laplace. So I'd say we're about halfway done with Laplace transforms. But today we're starting something new. So we're starting step functions, which, you know, I think today's kind of the first time you'll really get to see kind of the real benefits of using Laplace. Because you'll see the problems we're going to do today. Technically, you can do these problems in the classical method, but it's very cumbersome to do so. And so with Laplace, you can handle these. You know, I kind of call them kind of unusual forcing functions. You know, with a little bit more grace than the usual method. Okay. All right, and so with that said, remember to keep working on homework 3. So homework 3 is due next Friday. So you should be able to do the first 3 problems or most of it, maybe not some of the short answer questions. But these problems do take a bit of time, so you want to make sure that you're giving yourself enough runway to do so. So what we're going over today and Tuesday and next Thursday, those are mostly helping you for problem 4 and problem 5 on homework, as well as just a couple of the conceptual questions. And so those ones don't take as long, but you want to make sure you get problem 2, problem 3 done, because those can take a bit of time. Okay. All right, any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. Okay, so topic for today is step functions with Laplace transform. Okay. So first, let's do a little bit of motivation in terms of what is a step function and why do we care about it as an integer, right? So a step function is a step function is basically a function that has its value abruptly change from 0 to 1 at a given time. And just a little bit of trivia. So this is not important for this class at all, but for if you ever see this concept outside, I guess the person who invented the step function or first formalized the theory was some guy named Heaviside. And so this step function is sometimes named after him. So it abruptly changes its value from 0 to 1. At a given time. Okay. And so if you plot it out, right? So if you plot out the step function for all time, it looks like a step, right? It looks like a step that you would take up from stairs, hence its name, right? And so the usual symbol that we give for the step function is u. Okay. So u is a function of time. And then always accompanying the step function is the time in which the step occurs. And so the way we denote that is with some constant here, right? So we say u of t minus t naught, where this t naught, this right here is the time where the step occurs. Okay, so if you wanted to plot it, so horizontal axis here is time, okay? So at a given time, so we'll say that t naught is given by this value right here, right? So the step function kind of comes along all the way up until t naught has a value of 0, and then right at t naught, it just kind of shoots up as a vertical line, and then it continues on like that, right? So the value of this step here is canonically 1. Okay, so a step function is what I kind of characterize as a special math function. So it's a function here that doesn't have the same properties as a typical function. Like, if you try to take the derivative of the step function, you would basically get 0, and then all of a sudden it becomes infinity at t is equal to 0 because you have a vertical line. So it's not really a traditional function. It's a special function that's used for certain applications. Okay, and what are those applications? Exactly. That is one good application. So step functions can be used to model a phenomenon that is suddenly turned on or turned off. Okay. All right, and we see a lot of these in engineering, just because the way a lot of engineering systems are designed. We have a lot of engineering systems that in the most obvious case, we have systems that have an on and off switch. But there are other cases too where you have a situation where you're applying the loading and then you're pulling away, applying it and pulling away, right? So, the most obvious case, is you see this application a lot in circuits. Okay. So you might have a situation where you have a circuit that's in charging mode versus discharging. Right. So think of your phone, right? So if you think of your phone, when you're plugging it in, it's charging. The circuit is kind of acting in a certain way where the amount of power is building up in your phone as you're charging it. And then when you unplug it, right, then your phone is discharging energy as it's using it to run the phone functions. Right. So in the charging state, your phone, or some circuit may look something like this. Right. So you have a circuit here. This is just a simple RC circuit we've connected to a DC battery. Okay. Right. And so the differential equation that corresponds to this is dq dt plus 1 over RC times Q is equal to E over R. Okay. Right, and if you solve for its solution, Q of T is equal to E over R multiplied by 1 minus E to the minus T over RC. Okay. So I believe this was an example we did, maybe a few weeks ago when we talked about first order equations. Okay. Okay. But you could very easily, take the same circuit, right? And then basically just disconnect the battery and connect a wire instead, right? So in a discharging state, your circuit may look like the following. Right? Where your differential equation changes, right? And your solution will change as well. Okay? Right. So for that second system, we don't need integrating factor for that one. We don't need so this one you can just solve with simple separation of variables, right? But we have, you basically have a situation with two very similar systems, but because there is a difference in in how the battery is connected to them, technically they have two different governing equations and two different solutions. Okay. Now, if you were to examine a situation where, maybe you have a system where you're plugging the battery in, you're unplugging it, you're plugging it, you're unplugging it, you're kind of doing this over and over again, right? That kind of system to kind of solve for its behavior would be very cumbersome using these methods, because every time you make a change in the system, you unplug the battery, you plug it back in, right? It changes your differential equation. So every time you do so, you have to solve a separate, a separate differential equation. Okay. Which you could do, and before people started using Laplace transforms for differential equations, that's essentially how it was done. But you can imagine how it can be pretty cumbersome if you were kind of plugging in the battery, unplugging it multiple different times. Okay. Now the advantage of using a step function is that besides the battery, nothing else in the circuit really is changing. The only thing that's changing, if you even look at our governing equation. The only difference between our equations is what's happening on the right-hand side, right? So it either has a value or it's zero, okay? So a situation like this is actually perfect to model with step functions, right? Because step functions are either zero or they're one, right? And so we can use that to model these types of situations and solve it in a unified kind of one step, essentially. So you don't have to keep kind of going back and forth between these two equations. Okay? Right, and so that's very appealing, right? Especially when you have these engineering systems where maybe the system itself isn't changing all that much, but the amount of forcing or the amount of power that you are supplying is either going to be present or okay. And like I said, there's a lot of applications for this in engineering. Okay, and the reason we have to use Laplace is that like I mentioned before, the step function is not really a traditional math function where you can kind of take its derivatives and plug it in like a normal math function, right? And so even if you were to account for it on the right-hand side, you can't really apply one of our traditional methods like undetermined coefficients because, it doesn't really behave like a normal function. Okay? So Laplace, because of the properties of Laplace, it really kind of gives us the ability to, handle these situations. Okay. All right, so that's the motivation, right? And so, you know, with these step functions, we can use it for these applications here. Any questions on this so far? Okay. All right, so let's get to some of the mathematics. So let's find out first of all, you know, what is the Laplace transform of a step function? All right, so we're basically going to take the Laplace transform of u of t minus t naught. All right, so let's plug it into our Laplace transform formula. So we have integral from 0 to infinity of e to the minus st u of t minus t naught dt. Okay. And so because our step function here is kind of a strange function, you know, it doesn't really have an integration that we can take, okay? But the step function does alter our integral, right? Because remember, the step function has a value of 0 when t is less than t naught, and has a value of 1 when t is greater than or equal to t naught, okay? Right, so with that in mind, you know, let's use that information to break up our integral, right? And so, you know, one of the kind of core tenets of integration, right, is that if you have integral from, you know, a to b, right, or let's say that, you know, a and b exist on a number line like this, right? If you put some intermediate point between there, so let's say we put a point C that's in between, right? Right? Then what we can do is we can break up that integral. One integral from A to C and another integral from C to B, and then add them together, right? And so this is integral from A to C of dot 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 dt plus integral from C to B dot 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 dt. So basically, you know, we're just taking our entire integration bound, we're breaking it up into two segments, integrating those separately, and then adding them together, right? So you can do that at any time, as long as the value C is in between A and B, right? So let's use that property here to simplify our integral, because we know that, you know, this step function has two distinct values, okay? So let's break up this integral into one portion where we integrate from 0 to t naught, right? And we know the value for u at that time is 0. So we have 0 multiplied by e to the minus st dt, okay, plus integral from t naught to infinity of 1 times e to the minus st dt. All right. So of course the part with 0 is going to go away, right? And so integration of, well, we take 0 times e to the minus st, that's 0. And we take integral of 0 is just 0. So that part's going to go away. And so all we're left with is just integral from t naught to infinity of e to the minus st, okay? So just like we did before, we're going to integrate this. And so that is a minus 1 over s e to the minus st evaluated from t naught to infinity. So we plug in the integration bounds here. First, we have e minus 1 over s times e to the minus infinity. And so e to the minus infinity, of course, is going to be 0. Okay. And so all we're left with is 1 over s e to the minus s t naught. All right, so that is our Laplace transform there. Okay. So let's take a look at this function here, right? So we have something, we have one familiar component here, right? So we've seen this 1 over S before. Right? So from before, we know that 1 over S is the Laplace transform of 1. Right, I believe that was the very first Laplace transform that we did. Okay. So that makes sense, right? Because our step function here ultimately has a value of 1 once you kind of move past the step, right? And so it makes sense that we have a component that looks like Laplace transform of 1. The other component here, e to the minus s times t naught, right? This is an additional term that we're adding, and you can see that the additional term is very closely related to where that step takes place. Okay. So when you look at it from that perspective, the Laplace transform of a step function is really just, an additional step beyond our Laplace transform of 1, right? So we just add that e to the minus s t naught there, okay? In fact, that this whole idea of multiplying by e to the minus s times t naught, that's kind of the whole central tenet of what's called the second shifting theorem of Laplace. So we've already gone over the first shifting theorem. So the first shifting theorem is what we call an S shift, right? So essentially, remember, just to kind of refresh your memory, if you multiply by e to the minus at in the time domain, that results in a shift of a in the Laplace domain. Okay. So the second shifting theorem is kind of the opposite of that. So second shifting theorem is often called the T shift. Okay. So this T shift basically states that, if you multiply by an exponential term in the Laplace domain, that's going to end up as a shift in the time domain. All right, so that's kind of the the word definition of T shifting. But let me give you the formal kind of mathematical definition. Okay. So let's say that we have some function f of t where we know it's Laplace transform. So we say that Laplace transform of f of t is equal to f of s, right? So our base function f of t and its Laplace transform are known, right? So we know what that looks like, right? And so if we take e to the minus as and multiply that by f of s, okay? Then that's going to result in a shift in the time domain. So then e to the minus as multiplied by f of s is equal to Laplace transform of f of t minus a multiplied by the step function u of t minus a. Okay. All right, so the thing to be careful with the second shifting theorem is that, I think by this point, especially if you're kind of been keeping up with the homework, right? You're used to kind of applying the first shifting theorem. So in the first shifting theorem, let's say that, we have some function f of t, right? And its Laplace transform is f of s, right? And so what we found is that e to the minus at f of t, okay? Right? We take its Laplace transform, we end up with f of s plus a, right? So notice kind of the subtle difference in the sign here. So in our first shifting theorem, we multiply typically by a negative exponential, right? So our coefficient there has a negative sign, and that ends up as a positive shift in the Laplace domain. Right? So the sign is different, right? But for the second shifting theorem, the sign is the same, right? So we multiply typically by a negative exponential in the Laplace domain, and then that ends up with a negative shift in the time domain. It's very subtle and I think very, very easy to make mistakes, but you definitely want to make sure that you kind of catch them. Okay. Okay. All right. So let's do an example, right? Just so you can kind of see how this works. Okay. So let's take a certain function. So let's say f of t is equal to 5 sine of t. Okay. All right, so this is just 5 multiplied by one of our base functions. So this is one that we can Laplace transform using our table. And so we take its Laplace transform, we get f of s is equal to 5 over s squared plus 1. Okay. Okay. So then let's see what happens if we want to apply a t shift to this. And so let's say that instead, right, we take e to the minus 2s, okay, and we multiply that by f of s, right? And so this gives us 5 e to the minus 2s all over s squared plus 1. And then now the problem is, now that we have this shifted, well, let's say that now that we've multiplied our Laplace transform by this exponential, now the task is to let's find the inverse Laplace of this shifted term. Okay, so let's just use our second shifting theorem. So this is just a direct application of the statement that we just made above there, right? So we know little f of t, we know big F of s, right? So we multiply e to the minus 8s times f of s, then, the result that we get is going to be our original f of t, but basically everywhere we see t, we're going to replace it by t minus 2 in this case. Right? So this e to the minus 2s, this is going to apply a shift of minus 2. Right, so that's going to cause a shift of minus 2 in the time domain. So in our original f of t, everywhere that we see t, we're going to replace it by t minus 2. And the other thing we're going to do is we're going to multiply it by a step function with the same shift. Okay. All right, so since we already know f of t is 5 times sine t, right? So that means f of t, okay, We just shifted now. F of t minus 2 is equal to 5 sine t minus 2 multiplied by u of t minus 2. So that expression, that box expression, is the inverse Laplace of this guy. All right, any questions on this example here? Okay, good. Okay, so before we kind of move on, let's take a minute to kind of look at this function that resulted here, right? Because there's a couple things going on, right? And so on the one hand, we have our usual, or we have the function that we've been talking about for the first 30 minutes a day. We have our step function, okay? Right, so u of t minus 2. So the fact that that's there means that we have a step function that's being applied here, right? And so with the shift of only 2, this is telling us that this function f of t minus 2 is going to have a value of 0 up until t is equal to 2. So this essentially turns off function before t is equal to 2. Okay. And then after t minus 2, that step function becomes 1. So essentially it allows the function to exist after that. Okay. Okay, so if we plot this out, right? So we have f and t, right? So let's say that t minus t is equal to 2 is here. Okay? Up until t is equal to 2, this f is going to have a value of 0 because of that step function. Okay. Okay. So that's the first thing, right? So when a step function is present, that means it's not even going to be active until the step occurs, right? All right, so the other part to kind of notice here is we have sine of t minus 2, right? So this is a sine function, so nothing weird is happening in terms of that, right? The only difference here is that this sine function is going to be shifted to the right by an amount of 2. Okay. So what does that mean, right? Because we all know what sine of t looks like, right? And so if you draw sine of t, right, we know that sine of t starts at 0, and it kind of goes like this, right? Right, so this function here is sine of t. Okay. So what do I mean that the function is shifted by 2? Well, instead of the function starting at t is equal to 0, right, it's now going to start at t is equal to 2. Because, when you have sine of t is equal to t minus 2, what happens when you plug in t is equal to 2 here, right? You're going to get sine of 0, and we know sine of 0 is 0. Okay? And so visually what happens is that it looks like this entire function gets kind of shifted to the right, okay, by an amount of 2. And so if you actually plot it out, right, it's going to look like this. Actually doesn't look too bad. Usually I'm not very artistically, my drawings suck, as my wife would say a lot of times, but that doesn't look too bad. Okay. All right, so that's why we call this the second shifting theorem a shift, right? Because it literally takes our function and just shifts it to the right. Most of the time we're going to the right. Okay, and that's going to play an important role once we start using this with differential equations. Okay. All right. Any questions on this? Okay. Good. So that's kind of the basics of step functions and how to take its Laplace transforms. let's do something a bit more interesting now. So let's go over the concept of a square wave. Okay. So step functions are useful by themselves, right? So you can see that we can use them to shift a function to the right, but you can actually combine step functions to kind of do what we talked about at the beginning of class today. So to turn a function on and then turn a function off. Okay. And so if you actually plot it out, it ends up looking like a square wave, right? So let's say we have our function here. We have t is equal to t1 and t is equal to t2, right? So let's say that we want to turn on the square wave at t1, right? And then it's going to move forward, and then we're going to turn off the square wave at t2. Okay. So instead of having a function that gets turned on at a certain time and is on for all eternity, we let this function be turned on at t1 for a set amount of time, and then finally we turn it off at t is equal to 2. Okay. So we can do this with a combination of step functions, right? So we need one step function to represent the portion where the function is turned on. Okay? So we have u of t minus t1. Okay. Then we need another function, which is going to turn off the function at t is equal to t2. So we need another step function there. So we need a u of t minus t2 here. Okay. But in order to kind of combine their effects into a square wave, we're going to take the difference between them. We're going to take u of t minus t1 minus u of t minus t2. Okay. And that quantity will produce the square wave above. So I'll write it down here again, just to kind of make it a bit more clear. So square wave is u of t minus t1 minus u of t minus t2. Okay. So once again, let's see how this is done in an example. Okay, so let's say that we have a function f of t, and it's a piecewise function, and so it's going to have different values on different time intervals. Okay. So let's say f of t is equal to 0 when t is less than 0. It's going to have a linear ramp when 0 is less than t is less than 5. And then after t is equal to 5, the function turns off again. Okay. So what we want to do in this problem is we want to express this piecewise function as a single function using step functions. Okay. All right, so let's look at kind of each interval here and kind of see how we can kind of represent. Okay. So first interval that we see is the interval of t is less than 0, right? And so before t is equal to 0, we're essentially saying that the function is 0, right? And so what we can say is that the function is off before t is equal to 0, right? Because there's just kind of no action. Right, so after t is equal to 0, up until t is equal to 5, we can say that the function is on, right? So it has a non-zero value. And then after t is equal to 5, the function turns off again. Okay. Right, so this pattern here tells us that, we should use a square wave to express this. And so our square wave needs to turn on at t is equal to 0. And then we need to turn it off at t is equal to 5. So this is kind of perfect for a square wave. Okay. Okay, so using the same kind of formula that we had up there for a square wave, right? So we're going to have u of t minus 0, right? So that's where it's turned on, minus u of t minus 5, which is where it turns off. Okay. And then we're going to multiply this by our function that we're turning on in between. And so we're going to multiply this by t. So let me just rewrite it, because typically or at least for my personal preference, I put the step functions at the end of the expression. And so we say f of t is equal to t times u of t minus u of t minus 5. And of course, we can plot this, right? This plot's pretty simple, right? Right, so if we plot this, we can see that from from t is equal to 0 to t is equal to 5, we have just a simple linear function, okay? And then after t is equal to 5, the function just kind of shuts off.
That goes to 1, right? That peak,
Second?
the peak is at 1.
No, it's 5, because it ends at t is equal to 5. Because the function is t, right? So when t is equal to 5, then f of t is 5. It's fine. Yeah, so the step function is 1, but then the function itself is t. So, it takes that value. That's a good point. Yeah, so the value of the function is whatever the function is. The step functions are really there just to turn it on and turn it off. Okay, good. So that's fairly straightforward, right? So, whenever you have discontinuous functions or piecewise functions, you can represent them as a single expression using step functions, right? And of course, we can then now take this and we can then take its Laplace transform. So let's see what that would look like, because there's kind of an extra step here that I think you may not expect fully. Okay. So first thing I'm going to do is I'm going to take this t and I'm going to distribute it to both of the terms. So we have f of t is equal to t u of t minus t u of t minus 5. Okay. Right, and so let's take the Laplace transform. So big F of s is equal to Laplace transform of t u of t. And remember, Laplace transforms are linear, so we can take each of these individually, minus Laplace transform of t u of t minus 5. Okay. So let's take these Laplace transforms. So the first term, the Laplace transform t u of t, that one's no problem, right? And so u of t is essentially just 1, right? And so, it doesn't really apply any shift. And so Laplace transform of this is going to be 1 over s squared. Now the second term. Right, so looking at this expression here, we can see that we're going to be essentially applying our second shifting theorem, except kind of in reverse, right? So, the way we introduce second shifting theorem, we multiply by e to the minus as we end up with a shift in the time domain. Here we're doing the backwards, right? So we have a shift already in the time domain that we want to Laplace, right? Okay. But there's something kind of unusual, right? So let me scroll up for just a second, right? And let's look back at the second shifting example that we did right before this. Okay. Okay, so when we applied our second shifting theorem to the sine, right? One thing to note here is that our base function and our step function, they had the exact same shift, right? So they both had the shift of 2. Okay. We come back to this example here. We have a Laplace transform of t multiplied by t minus 5. This does not have the same shift. So our step function is shifted to the right by an amount 5, but our function here is just plain old t. Okay. So we can't actually apply second shifting theorem to this just yet, but we can, apply an algebraic manipulation or a twist on the second shifting theorem. Okay. Right. So I would say this is kind of the second form of the second shifting. It's still the same second shifting theorem. Say that 10 times fast. But we're just going to apply a twist on it because this situation does happen a lot, right? So second shifting theorem. We'll call this part 2. So let's say that you want to take the Laplace transform of f of t and u of t minus a, right? So that's exactly what we have here. So we have some function of time multiplied by a step function, and their shifts do not match. So the way that we take this Laplace transform is we kind of pre-multiply by the shift, right? And so we have e to the minus as. Okay. Right, so that e to the minus as is going to account for the shift. And then you're going to take the Laplace transform of f, but you're going to apply the shift in reverse. Okay. And you're going to take, this is multiplied by the Laplace transform of f of t plus a. So essentially, you're kind of applying the shift in reverse in order to get those shifts to kind of match up between the f and the step function. Okay. So what does that look like for this example here? So let's apply that to this Laplace transform of t multiplied by u of t minus 5. Okay. And so since these shifts don't match, let's apply the second shifting theorem, or the part 2 of it, right? So we're going to multiply by the e to the minus as, right? Because remember the step function, we can't really change all that much, right? And so we kind of have to conform our function f, to match that shift, right? So no matter what, we're going to multiply by minus e to the minus 5s, right? So that's going to account for the shift in the step function. And then from there, we're going to multiply by the step function of t plus the shift. Okay. So instead of taking the Laplace transform of just t, we're going to take the Laplace transform of t plus 5. Okay, so we're essentially reversing the shift. And that we can do, okay? Because remember, Laplace transforms are a linear process, and so this is equal to e to the minus 5s multiplied by Laplace transform of t plus Laplace transform of 5. All right, so we can do both of those, right? And so this is e to the minus 5s multiplied by 1 over s squared plus 5 over s. Right. Why I keep using the number 5 for these examples with Laplace, I have no idea, but I have to be very careful with how I draw the number 5. Okay. All right, and with that, that's the answer to this. And so, if we combine that together with our previous one, okay. So then Laplace transform of t u of t minus t u of t minus 5 is equal to, right? We can't forget our Laplace transform of t u of t, so that's 1 over s squared. Okay. And then we're going to add what we just, or subtract what we just computed here. Okay. So we're going to subtract e to the minus 5s over s squared minus 5e to the minus 5s over s. All right. Any questions on this? Okay. All right, so let's do another example of this, just because it's this is another one of those things where you kind of just have to keep practicing it. Let's do one that's a little bit more complicated. I probably won't do this one all the way. I'll kind of just like kind of outline the steps and kind of where you need to apply the shifting. But it's good to kind of see a complicated example like this, just so that you kind of know what to do. So once again, we're going to have a piecewise function. So ft is equal to. So let's say that this function here has a value of 2 when t is between 0 and 1. We'll say that it has a value of 1/2 t squared, so t squared over 2, when t is between 1 and pi over 2. All right, and then when t is greater than pi over 2, f of t is equal to cosine t. So cosine t when t is greater than pi over 2. Okay. And although it's not explicitly stated, right, and so sometimes, a lot of times you'll see functions just like this. Even if it's not explicitly stated, wherever the function of t is not defined, you can assume to have a value of 0. Okay. So, the only section of time here which is not defined is when t is less than 0. Okay. So kind of the implication or the implied value is that f of t is equal to 0 when t is less than 0. Okay. So even if it doesn't state it, you can kind of just apply that if it or imply that if it's not explicitly stated. Okay. So let's do the same thing we did in the previous example. So let's express this f of t as a single expression using step functions. Okay. And then after that, we're going to take its Laplace transform. Okay. All right, so there's not too much new with this example. It's just kind of the same thing, just a little bit more steps involved. So let's do the first thing. So basically, for every section of this piecewise function, let's apply a square wave or a step function. Okay. All right, so we have three segments here. So two of them are going to require square waves because those are sections that turn on and then turn off. The last section, cosine of t, that's a section that just turns on at t is equal to pi over 2. So we don't need to turn that one off. Okay. Okay. All right, so we can say f of t is equal to 2. First, we have 2, which is a constant. So this section of the function here turns on at t is equal to 0. So you have u of t minus, and this function turns off at t is equal to 1. So we're going to subtract u of t minus 1. All right, and so to that, we're going to add our next segment. So our next segment is t squared over 2. This segment here turns on at u t minus 1. Okay. And it turns off at t is equal to pi over 2. So we're going to subtract u of t minus pi over 2. All right, and then finally, we're going to add our last segment here, which is the cosine t. Turn add cosine of t. Okay. And this simply just turns on at t is equal to pi over 2. So this is multiplied by u t minus pi over 2. All right, so that's step 1, right? So we've expressed this function as a single expression, right? So next, let's take its Laplace transform. All right, so to take its Laplace transform, first thing we need to do is distribute. So f of t, we're basically going to distribute every function, and so we get basically 5 different pairs of function and step function. Okay. So it's equal to 2 u of t minus 2 u of t minus 1 plus t squared over 2 u of t minus 1 minus t squared over 2 u of t minus pi over 2 plus, I always just run out for the cosine. Should shift right here. Cosine of t u of t minus pi over 2. Okay. Okay. All right, so we have 5 pairs here, right? So we have 2 pairs for the first segment, 2 pairs for the second segment, and 1 pair for the final segment. So let's take each Laplace transform individually. Okay. So first we have the Laplace transform of 2 u of t. Okay. So this one's very simple. So this, there's no shifting required for this one. So this is just simply 2 over s. Okay. Next term that we have there is a minus 2 times u of t minus 1. So we do have a shift here. So we do have a shift of 1. But our function here does actually not depend on t. Okay? So our function here is just a constant. So we actually don't need to do any kind of weird shifting shenanigans here as well. So from here we can just do a minus 2 over s. Okay. But we do need to multiply by the exponential. So this is minus e, or multiply e to the minus s. But those first 2 terms, very straightforward, because that function there does not really depend on time. Okay. All right, so let's come to the next one. So I'm only going to do one of these just because they're both kind of the same. But we have function of t squared minus 2, t squared over 2 multiplied by ut minus 1, right? So here we do have to apply a shift, but we have the same situation as the last example where the shift of our function and the shift of the step function are not the same. So let's apply our second shifting theorem, before we take the inverse Laplace. Or the Laplace transform, excuse me. Okay. So to do this, we're going to get e to the minus s, that is the shift, multiplied by Laplace transform of the opposite of the shift. So everywhere we see t, we're going to apply the opposite shift. And so this is going to be t plus 1 squared over 2. Okay. So let's factor out that 1/2. So that 1/2 is not going to change our Laplace transform. So we can pull that out. And then let's FOIL out the squared term there. Okay. So we have e to the minus s divided by 2 multiplied by Laplace transform of t squared plus 2t plus 1. Right, and so we can take the Laplace transform of each of these individually. And so that's e to the minus s divided by 2. We have a Laplace transform of t squared, so that we know is 2 over s cubed. Okay. Plus 2 times t, so that's Laplace transform is 2 over t or s squared. Plus Laplace transform of 1, which is just 1 over s. Okay. And so that right there is our Laplace transform of that second term. So their second term, this is a good example of us having to apply the same second shift. Okay. Okay. So same thing applies for this one, except the shift is obviously different. So just like we did with that one, we have mismatching shifts. Okay, so we're going to apply second shifting. I'll let you kind of fill in that one because the process is essentially the same. And so you end up with a very similar result, but just the coefficients are different because the shift is different. Okay. All right, last one we'll do together is this cosine t multiply u of t minus pi over 2. So this also has mismatching shifts. Okay. So same thing we did there. Let's apply our second shifting theorem and take this Laplace transform. Okay. All right. So just to kind of make it clear, I'm going to move it down here. Okay. So we have Laplace transform of cosine t multiplied by u of t minus pi over 2. Okay. All right, so first thing we're going to do is we're going to apply our shift, right? So we have e to the minus pi over 2 times s, okay, multiplied by the Laplace transform of cosine. And since we applied that shift to our function, we're going to replace t with t plus the shift, right? So this is cosine of t plus pi over 2. Okay. All right. So from here, you can take this Laplace transform. It's not the easiest to do because the shift is inside the cosine, but you can do it. But one way you can make it much simpler is you can use some trig identities. Okay. Don't panic. Trig identities is not something I expect you guys to memorize, right? Even this one is one that I check and make sure that I know what I'm doing. So this is the reason I kind of do this with you guys is sometimes you have to kind of rely on these kind of identities or tricks to kind of make things simpler. Because when you apply shifts and they're kind of embedded into these kind of complex functions, then oftentimes it's much easier to kind of rely on an identity to make it simpler. Okay, but based on a trig identity, this cosine of t plus pi over 2 is equal to minus sine of t. And so this is Laplace transform of minus sine of t. Okay. Right, you're essentially taking cosine and you're shifting it by a half cycle to the left, right? And so that's why you end up with a minus sine of t. Okay, so we take its Laplace transform. Laplace transform of sine of t is something that we know. Okay. So this ends up being minus e to the minus pi over 2 times s times Laplace transform of sine, which is 1 over s squared plus 1. Okay. All right. Any questions on that example there? Okay. All right. So for the last 10 minutes here, let's do a couple more examples going the opposite way. I wanted to do an ODE example today, but I don't think we'll finish it. So I think we'll probably save that for Tuesday, along with our discussion of the impulse function. Okay. Okay, so let's do a little bit of practice of going the opposite way. Okay, so first let's find the inverse Laplace of the following function. Okay, so we have f of s is equal to 1 minus e to the minus 2s all over s squared. Okay. We have two terms in our Laplace transform here, and we want to take its inverse, right? So easiest thing to do here is to first of all split these into two terms completely. Right? So you have f of s is equal to 1 over s squared minus e to the minus 2s all over s squared. Okay. So all I did there was just kind of split these into two terms, just so it's a bit easier for us to see and take the inverse. All right, so now we're ready to take the inverse. All right, so f of t is going to be equal to Laplace inverse of 1 over s squared minus Laplace inverse of e to the minus 2s over s squared. Okay. So the first part of this is obviously very easy to take the inverse. You know, we've seen this before. So 1 over s squared is just the Laplace transform of t. Okay? So we take its inverse, we end up with just t. Okay. All right. And then we're taking the Laplace inverse of a term that, you know, that obviously has a shift. Okay. Now I'm going to show you kind of the way that I kind of do these and kind of the mindset that I use. It kind of works for me. But you know, there's other ways to kind of think about this as well. Okay. So when I see a part like this where I have to take the inverse Laplace of something that has a shift, what I like to do first is take the Laplace inverse of the base function. Right. So for this expression right here. Right. So step 1, take inverse Laplace of base function. And that is without shift. Okay. Right, so that's going to give you some function of t, right? So hopefully there's a table value there that you can do. Okay. And then after you take that, right, then you can apply the shift to that function. Right, and so what kind of results from this mindset is that whenever you see a shift, or whenever you see an exponential term in the Laplace domain and you're looking to take the inverse, you know, essentially what I do is I essentially just kind of block it out. I kind of pretend that it's not there, okay? And so I just take I take the inverse Laplace of the terms that don't include that exponential, and then after I do that, then I apply the shift to it. Okay. All right, so for this function, we can see that the base function here without the exponential is just 1 over s. Okay. All right, so the base, or 1 over s squared, excuse me. Right. So we know that's inverse, and so the inverse of 1 over s squared is just simply t. Okay. Right, and then after we do that, now we can apply the shift to that. Okay. And so we apply the shift of -2. So that means that we replace t with t minus 2, and we're going to multiply it by a step function, u of t minus 2. Okay. Okay, and so the inverse Laplace of that function there, f of t, is equal to t minus 2, u of t minus 2. Okay. And by the way, even though it's implied, so you don't have to do this, right? And so I'm not going to mark you right or wrong either way. But technically, you know, if you have just a function t like this without any step function, you know, typically it's customary to also add this, you know, a base step function there as well. All right, so even if this is implied, okay, customary to also but again, it's not something, you know, I'm not that strict about it. So usually if I see just the function by itself, you know, the implication is that it starts at t is equal to 0. So there's really no need for that u of t there. But you know, but you know, it looks nicer too, right? To have some set that every functional part has a step function part. But you know, it's not something that I'm too strict on. All right. Any questions on this? Okay, I think we'll probably call it here. So we'll end a little bit early today because it's a bit, you know, I don't want to start a differential equation just yet. So when we come back on Tuesday, you know, we'll start by solving differential equations involving these step functions. So we'll do a generic example, and then we'll do an example with circuits, and then we'll move on and talk about impulse functions. Okay. All right. So thank you guys for coming today. I hope you guys have a good rest of your day. Stay warm. It's very cold outside, and I will see you guys next week.
Just a question on this one.
Sure.
This one you did do? Does this look about right?
Yep, exactly. Yeah. So you replace the t with t plus pi over 2, you square it. Yep, perfect.
Okay. Yeah, this would be like a lot easier.
Yeah, exactly.
Thank you.
Yeah, the next class is calculating for yeah. I've got a bunch of stuff in there, so it's
You too, Anthony.